I'm going to talk about Assignment 2 tonight. Welcome to Module 15. This is the first module in which we are going to talk about estimating the cost and the size of the software. Last week we talked about estimating the size, and this week we're going to talk about the effort and the cost, I should say. And we're going to continue that for 2 weeks, this week, and actually next week is spring break, and then the week after that we're going to continue. Now, for those of you who slept through all of the snowstorm or whatever last week, we recorded last week's session on Wednesday, and it's available online, and I gave you instructions on how to get access to it. And if you haven't yet, you really need to see it because that has all the information you need to do Assignment 3. But anyway, tonight we're going to talk about effort estimating, which is part of Assignment 4. One other thing I wanted to point out is I'm going to talk about my preliminary assessment of your Assignment 2s. I already got Assignment 2 from most of you, and I started looking at them over the weekend. And I found certain patterns that I want to go over. So I'm going to do that a little bit later this evening. Okay, we're going to begin our discussion of effort estimation with this module, which gives an overview of effort estimation issues. We're going to talk about how you measure effort. You recall that we talked about how to measure size and different ways of measuring size. Well, now we're going to talk about ways of measuring effort. We're going to talk about how that relates to the schedule, and then some general points, and then in the next module we'll get into more specific details. So we've moved on. We're finished with the estimate size box, which becomes Assignment 3, and we're going to get into the estimate effort and cost box, which is Assignment 4. Now, again, if you haven't looked at the schedule lately, Assignment 4 is not due until after the midterm exam, but this topic will be on the midterm exam. So the midterm exam will cover everything up through and including the estimate, effort, and cost box, which is this week, and then one more week of lecture will be on the midterm exam. I'll say more about that later. This is what's inside that box. If we take this box here that has the blue boundary around it, it says estimate, effort, and cost. And if we look inside that box, here's what it looks like. You take the information about what you have to do, which is usually organized into your work breakdown structure, and you extract from that all of the tasks that happen to deal with actual software development, such as designing the code, writing the code, testing it. And then you estimate the size and then the effort. Now, we talked about estimating the size last week. Now we're going to talk about estimating the effort. When you do estimate the effort, then you convert to cost in terms of dollars or pounds or whatever your unit of money is. And given that information, then you can estimate all the other costs, things that are not directly software and development costs, such as travel costs, management costs, overhead costs, training costs, and all these other kinds of things that you need to do. And that's because often, although not always, they are estimated as a percentage of the costs above. For example, the cost of training people might be 2% of the cost of developing the software or something like that. We'll talk a little bit about that later. Let's start by talking about how you would measure effort. Effort is the amount of labor required to do the project. And it's measured in things like staff months or staff hours or person days or man days or per whatever. It's a combination of a unit of work, a person, and an amount of time. Now, those of you who've studied engineering or physics know that the way you measure work is energy over time, and that's what we're doing here. A person month or a staff month is one staff member working over the period of 1 month. So it's the same idea. A month is a measure of time. A staff month is a measure of effort. And it's important to understand the difference between those two. If 3 people complete the job in 1 month, that's a 3 staff month job, but a 1 calendar month job. Because it takes 3 people to get it done in 1 month. So it's important to understand the difference. A month is a measure of time. A staff month or person month or man month or whatever is a measure of work or effort. Now, one of the problems with measuring effort is that it's hard to define it precisely when the workers are people. And one of the reasons for that is that people don't just work constantly. They take breaks, they take time for lunch, they take vacations, and things like that. So here's a little example. You have 2 people, they're both executives of 2 different companies, and one of them says, we do 50 web pages per staff month. You only do 40 web pages per staff month, therefore we must be better than you. But the guy on the right says, how do you measure a staff month? And that's important because how you measure it determines what you're actually figuring out. So let's talk about hours, days, and months, and in particular staff days, staff hours, and staff months. It's important to understand the connections and the relationships here and the ways people can fudge these relationships. And the reason that's important is if you are estimating for your organization, you have to know how your organization measures and be consistent with the way your organization measures things. If you do that, then you can look at data from previous projects and estimate new projects. On the other hand, let's say you have a supplier and you're getting, remember we talked in the last lecture about free and open source software and off-the-shelf software and software you buy from a supplier. If you buy software from some other organization, you need to know how they measure these things so that you can understand what's going on. So let's talk about this. Conceptually, a staff hour is a person working for an hour. Seems simple enough, right? And a staff day is a person working for a day. So how many staff hours are there in a staff day? Well, I suppose it depends on how many hours people work. But it also depends on how you count hours. For example, I once did some work for the New York Stock Exchange. They calculated that a person works for 6.5 hours a day. Why? Because the rest of the time they actually spend at work was spent doing things like taking breaks, walking between offices and not doing any useful work while you're walking between offices and things like that. That was their way of measuring. Many organizations assume 8 hours per staff day, at least in the U.S. Now, I once talked to a guy who had worked in Korea, and over there it was more like 10 was the normal assumption. And if you go to certain countries in Europe, it's more like 7 or 6 because of the way their methods of counting people work. The other thing you have to ask yourself is, what about overtime? If somebody works 10 hours, but your normal workday is 8 hours, do you count that as 10 hours or do you count that as 8 hours? Well, what if you don't pay for overtime? Do you still count it the same way? How do you handle lunchtime? Is lunch added to the 8 hours or is it included in the 8 hours or the 10 hours or whatever. It turns out that different organizations do it differently. Different companies do it differently. In different countries, the norm is different. And what counts is different. Here's a simple example. At SMU, when you go to a class that's 50 minutes long, they count it as 1 hour. But it's really only 50 minutes, right? So you really only get 50 minutes worth of teaching, even though it's counted as 1 hour of teaching. Now that's because that's the system SMU uses. A number of years ago, I visited Ohio State University, and theirs was only 48 minutes per class instead of 50. Why? Because they have a big campus and they needed more time to get between buildings, between classes. So they allowed more time. Well, it depends on how you count as to what you're actually doing. Now, how many staff days per staff month? Well, in the U.S., the number that most organizations use is 19. Why? Because they subtract off holidays, vacation days, and sick days. And if you subtract that out from the average month, and they also subtract off weekends when people don't work, it turns out that the average month, the average employee works 19 actual days, if you don't count vacations, holidays, weekends, etc. But sometimes organizations don't give as many holidays, and therefore they maybe go up to 20 or 21. Maybe you are in a place where it's slave labor and you work every day and you don't get any weekends off and you don't get any holidays or anything, and then you might be 29 or 30 days per average month. Some months are longer than others. We just finished February that only has 28 days, and we're entering March that has 31 days. So in March, there's 3 more potential work days. So again, you have to know what your organization does. Now let me give you an example of something that you might run into. You are bidding on a contract, and you calculate that it's going to be so many staff days of work to get the job done. And this is based on, let's say, 8-hour days. Your competitor assumes 8.5-hour days. And therefore, they can bid a slightly lower number of days. In other words, your competitor is going to pay the employees the same amount, but make them work a half an hour more each day. So it appears as though they're cheaper. But maybe they are and maybe they aren't. When you do work for the U.S. government, they determine how many hours a day you have to use because they don't want companies fudging these numbers in order to be more competitive. They want everybody to be using the same numbers. But you have to know what you're dealing with here, because let's say you are talking to a potential customer and he says your competitor can do it in fewer hours, like the 2 golfers that I showed earlier on the slide. Maybe it's because of the way they're measuring it, and it's not really that different. How many hours per month, or staff hours per staff month? Well, if you multiply 8 by 19, you get 152. But if your company assumes 8.5 hours, or 9 hours, or 10 hours, you're going to be up into one of the higher numbers. Or if you're one of the lower numbers, you can be lower. It may depend on which month it is. February being shorter than March, for example. What is the length of a work day? How many hours do you actually have people working? What do you do with overtime? How many vacations and holidays do people get? How do you allocate management overhead? Sometimes that's factored into this. I was once giving a talk on this in Wisconsin, and they told me, yes, the shortest month of the year in Wisconsin is October. I said, October is a long month. How come it's the shortest month? And they said, because the first Monday of October is the start of hunting season, and therefore everybody takes a week or two off. Now, I went and taught another course in Munich, Germany one time, and they said, our shortest month is August because most people take their vacation in August. So you have to know what you're dealing with in order to use these numbers correctly. The most important factor is consistency. If you are consistent in how you measure these things from one project to another, then you can look at what happened on the previous project and draw reasonable predictions about the next project. If you don't measure consistently, then you really can't utilize the information from previous projects. It's just like size. We talked about how important it is to have a consistent measure of size. You also have to have a consistent measure of work in order to make meaningful predictions. If you can measure hours, because it's harder to get them wrong, it's harder to fudge them, it's harder to make bad assumptions about that. But many organizations, for example, use staff months. They estimate effort in staff months. And if that's what they do, you have to say, well, how many hours is in a staff month so that I can measure it correctly? Now, one of the problems that you run into, and it can really hurt you if you're a software manager, is people didn't report the truth on the previous project. For example, you say, how many hours did you actually spend doing this task? You reported 83 hours. And the guy says, well, we had a lot of unpaid overtime on that, but we didn't keep track of it. Because we don't pay people for overtime, we didn't keep track of it. So even though it was reported as 83 hours, it actually took 102 hours. Now, let's suppose that's the case. Well, then what happens when you make an estimate for your project and you estimate, well, I'm doing something almost identical, so I assume it's going to be about 83 hours. But in fact, it's going to be over 100 hours because of all that overtime they worked on it the last project and never reported it. So you run into this problem that you're digging a hole for yourself. The way it's supposed to work is overtime is supposed to help you when your estimate was too low. You have overtime. You can make people work overtime in order to get caught up. But if you know in advance that they reported 83 but actually took 110 hours, then maybe you should be estimating 110 because otherwise you're throwing away your risk management. The whole idea of overtime is supposed to be a way to manage risk, not a way to pretend you didn't spend as much time. So it's important to find out what the truth is, and many organizations don't want to record this. And why don't they want to record it? Well, they don't want their employees to find out how much overtime they're working and then complain that they're not being paid for the overtime. This happens a lot in some industries. So one of the things you run into in any organization is that sometimes they don't want accurate data for various reasons. And so if you're going to be estimating, you need to cut through that and say, I want to know what the actual data really looks like so that I can make more accurate predictions. Here's some possible exam questions. Explain the difference between a calendar month and a staff month. And to explain it, give me a 3 calendar month project that needs 6 staff months of effort, and give me a 6 calendar month project that only needs 3 staff months of effort. So you ought to think about what would be an example of each of those. If you understand the difference between months and calendar months, or pardon me, calendar months and staff months, then you would be able to come up with an example. Show how to convert effort and staff hours to effort and staff months, and explain how two different organizations might convert that differently. And the answer there is, how many hours do they assume is in a day? How many days do they assume is in a month? Explain how projects might hide the actual amount of effort they spent. And the answer is they, for example, don't report overtime, things like that. Now let's talk about the relationship between effort and time. A staff month means a person working for a month. So if you have a project that requires 12 staff months, it can mean 12 people working for 1 month, 1 person working for 12 months, or 3 people working for 4 months, or all sorts of other combinations. Now, those of you in the classroom, can you give me an example of something you might do? It doesn't have to be software, where it would make sense to have 12 people work for 1 month. 12 people working together on something for a month. Yeah? Yeah. Right, it would have to be something they wanted to get done quickly. And if you're going to have 12 people working together, you want them to be very well coordinated, and you want the task to require a relatively small amount of interconnection between the two. So, for example, taking a big warehouse and unloading it and moving everything to another warehouse. That's an example of something where you might take 12 people together and have them all work together for a month. Now, what about something where the sensible thing to do would be to have 1 person working for 12 months? How about writing a book? That's an example. Something that involves creative work that a person typically does alone might be an example of a 1 person for 12-month project. 3 people for 4 months is probably more typical for a software activity. Typically, you wouldn't have 1 person working on a piece of software for 12 months. You could, but you often wouldn't. At the same time, you probably wouldn't have 12 people working on a piece of software for 1 month. You could, but you probably would find that it would be hard to coordinate them that closely. But the point of all this is, even though mathematically these are considered the same, in practice, some make more sense than others. And the reason I point this out is, I've seen people who do a calculation and they say, okay, I need 350 person months of effort to do this project. And the boss wants it done in 6 months. So they say, oh, okay, well, we'll just have 50 people and they'll work together for 6 months. Well, getting 60 people to work together for 6 months is not always easy to do. So the coordination may be, that might not be a realistic plan. Maybe 6 months is simply not enough time to get it done. Maybe it is. The point is, you have to think that through, and you have to say, does this make sense? There's a lot of flexibility, but only so much. In other words, if you have 3 people for 4 months, then maybe 4 people for 3 months is a reasonable alternative. But 12 people for 1 month or 24 people for 2 weeks, maybe not. It depends on what you're doing. There's a very good book called The Mythical Man Month by a guy named Fred Brooks. It's in one of the reference lists. And he talks about this and various other issues as they pertain to software, and talks about how people can make really big mistakes by doing this sort of thing wrong. Here's sort of an explanation as to why it becomes an issue. If you have n people, then the number of ways that people communicate among each other is n times n minus 1 over 2. So 1 person, unless they're schizophrenic, there's only no communication required. If there's 2 people, there's 1 communication path. This is why pair programming works well. 3 people, all of a sudden you have 3 communication paths. 4 people, you now have 6 communication paths. And the point is, it goes up exponentially. So it's roughly equal to n squared. So the idea is that when you have 30 or 40 or 50 or 60 people, there's a lot of overhead there. And that overhead is due to the communication that may be required. Unless things are organized in such a way that there's not a whole lot of communication between different teams. But the point is, this is the underlying reason why when you have larger groups of people, there's more overhead. It's the diagram, or the curve looks like the one shown on the slide here. And this diagram, or a similar one, is actually found in that Mythical Man Month book. And so the way he talks about it is the amount of management overhead goes up exponentially as the number of people goes up. Now, there's another factor. There's a model called the Kokomo model that we're going to be discussing a little bit later that shows how much time you allocate to get the work done versus how many staff days of work is required to get it done. And this curve essentially shows that there's an optimum point here. There's a certain length of time that results in the minimum amount of total effort, total work to get the job done. If you take longer, it goes up. If you take shorter, it goes up. If you take too much shorter, it becomes almost infinite. Now, it turns out that this is a law of nature. And what I mean by that is that pretty much anything that goes on in nature, you can draw a curve like this. A good example is when any kind of animal becomes pregnant. There's a certain optimum amount of time for the baby to come about. In the human, it's about 9 months. In an elephant, it's about 12 or 13 months. In a mouse, it's about 1 month. And the point is, if you try to make it last longer or make it last less, there's more risk and more trouble involved. The same thing applies to processes in nature. How long does it take for a volcano to erupt? How long does it take for a storm to get through its process? Pretty much anything that goes on in nature, they have found that there's this idea of an optimal time as a function of work. And nature tends to optimize. So if the optimal amount of time is a certain amount of time, then that's how long it tends to take. Because in nature, the tendency is to get things done with the minimum amount of work. So I won't go into the biology and all that that's involved here, but it's been observed over and over and over again that this curve is essentially true for just about any process. And if you make it too short, it becomes impossible to do it. Some things cannot be done faster than a certain amount of time. Now, there are ways to get around that. For example, if you change the process, if you find a better way to do it, you might move the optimal point to the left. If you find a worse way to do it, it moves to the right. Now, there's a guy named Larry Putnam who found a very similar curve. And let me point out one of the differences between, in fact, there's two differences between these two curves. The first one is the one here doesn't show the actual scale on the horizontal axis, and it turns out the left side of the scale isn't actually 0. It's something bigger than 0, and the reason is because he knew it didn't matter, you went to infinity. This curve, they actually go all the way to 0. So this curve appears to be shifted right from the one on the previous one, but it's actually not. It's just where the scale is. The other big difference, and there's an important message here. According to this equation, and the formula for this equation is right here, if you allow more time, it'll take less effort. And if you followed this equation, you'd say, give me enough time and I can get it done for 0 effort, or close, arbitrarily small effort. Obviously, that's not true. And so the question to ask yourself is, why did Putnam find a curve like this, whereas the Kokomo people found a curve that actually starts going up? And the reason is, how did they figure out what these curves were? There was no mathematical calculation that they did. What happened is, they took data from real projects, got a lot of projects, and graphed them, and then decided what shape curve fits the graph. What is the formula for a curve that approximates what the data looks like? Putnam was working in an environment where all the projects that he discovered were not given enough time. They were all under intense schedule pressure, so they were all toward the left. And therefore, he had a lot of data points to justify the portion of the curve that's over here. He had very few data points to the right. This one represents the optimal schedule. And so when Putnam had no data points over here, and he tried to fit this curve to an equation, he came up with an equation that would predict you keep going down. But in fact, the equation is wrong. Whereas the Kokomo people had data on both sides of the optimal, and therefore they were able to show that when you get longer than the optimal, it starts going up again. Now, the reason why this is an important thing to point out is because many times you will discover a formula or a model or a tool that claims to be able to predict cost or predict effort or predict size or whatever. And it's important to realize that that model was developed based on looking at data. And if they didn't have enough data, they could well have made a mistake in their formula. And like this one, if people used Putnam's formula and they actually have more time than they need, they will grossly underestimate how much effort is required to do the work, simply because they didn't have an accurate formula. The formula is not magic. The formula is not based on the laws of physics. The formula is based on doing a curve fit to some data. Many times in the field of estimating in particular, you run into formulas that are based on this sort of technique. They got a lot of data, did a lot of curve fitting to the data, and said, well, this curve seems to fit the data, therefore let's use this curve. But it may not work. So don't ever make the assumption that the model has to be right. The model may not be. The formula may not be right for your situation. All right, now what is the optimal schedule? Well, it depends on many, many factors. And the way people figure out the optimal schedule is they look at data from real projects. So if you had an organization and had done a number of software projects, you would collect data from a bunch of those projects, and by analyzing the data, you would conclude this is what the optimal schedule would be for such and such size project. And it would be specific to your organization, the way your process, your people, the nature of the kind of work that you do, and so forth. And that's the best way to get a really accurate estimating process. If you don't have that amount of data, then all you can do is use somebody else's data and hope that it's reasonably similar to yours. But that's all you can do. The experience factor. The models that are out there represent the experience of the people who develop the models. So a big thing to think about is, how much do I trust the experience of this person or the person who built this model for doing things that I have to do? Let me give you a simple little example. Let's suppose that you were trying to decide whether to take this course, okay? And you talk to somebody else, and they said, well, it took me about so many hours to do this assignment, and so many hours to do that assignment. Well, that doesn't necessarily mean it'll take you the same number of hours, right? Because you may be faster or slower than that person. It might help you get a rough idea, but it may be way off. Here's a good example. I have kept track for over 20 years for assignment 5 and how many hours people claim they spent on the course. The lowest number I ever got was 38 hours. The largest I ever got was 300 and something. Most people report somewhere in the neighborhood of 100 to 150. Now, the point is, I try to correlate the number they reported with the grade. And what I found out was those who tended to get the highest grades tended to get numbers in the low 100s range. Those who claimed 200 or 250, which doesn't happen very often, but when they did, it was usually either somebody exaggerating the numbers or somebody who just wasn't very good at whatever we're teaching here. Similarly, when I had students who reported numbers significantly less than 100, in almost every case, they didn't get a very good grade in the course because it obviously meant they hadn't really put much effort into it. So that's been my observation. So the real point here is that every organization is different, every person is different, and until you look at data from your own experience or your own organization's experience, you won't necessarily have data that's an accurate predictor of what it's going to take you to get the job done. Okay, your level, your schedule isn't necessarily determined by any of these formulas anyway. For example, your project manager may come up with a schedule and say, we have to get it done. This is what's, I've intentionally set up the Mr. Television project like this. The project manager says, I want it done in 12 months. I can tell you right now that if you use the techniques I teach in class to do the estimating, you will find that it's going to take longer than that. And the idea is you need to decide what to do about that. If the boss says 6 months and you say, I can't do it in less than 8 months, then you have to negotiate. Either you convince the boss to give you more time or you take some of the requirements and back off on some of them. Then we'll talk a little more about that. But the point is, sometimes you don't have total control. For example, the customer may want to do a review at a time convenient to them, not necessarily convenient to you. There's all sorts of factors that may influence the length of the schedule. Now, one advantage you have here is that when you're near the optimal schedule, you can go a little ahead or a little below without dramatically changing the amount of work you have to do. It's when you try to make dramatically different. In other words, if, let's say this is 8 months, and you think it'll take 8 months to do the job, and the boss wants it in 6 months. Well, if you calculate the difference between this curve and this curve, you say, boss, it's going to cost an extra 12% in labor hours if we do it that quickly. But maybe that's a negotiation point you can make with the boss. But if the boss wants it done way over here, you say, boss, there's no way that's going to be 4 times as expensive. And that's outside of our budget. Or maybe it isn't. So, you have to realize that you have some flexibility in your schedule. But you also have to be able to say, it's really going to take us more, and we have to negotiate something where we can actually do it. We can agree to do it. One of the ways to gauge your schedule risk, if you're a manager, is to say, what do I think the optimal schedule should be? What is my actual schedule? And if they're significantly different, then you have a schedule risk. And that might be something to take into consideration. If you have a schedule risk, maybe you need to start putting in some things to measure how close you are to your schedule and raise alarms if you're getting behind. Now, let's move back to effort estimating. The most important thing that's an input to the effort estimate is what you have to do, the tasks to be performed. Typically, this is found in the work breakdown structure. Now, in estimating a software project, you typically break those into categories. And here are some of the categories that I have identified. The pure software development tasks, the additional tasks that a software person might support but are not technically software engineering, such as system integration, supporting that activity even though that's somebody else's responsibility, maybe. Support tasks, things that are done to help achieve the first two, and anything else you have to do that isn't included in the first three. And then finally, costs that are not measured in terms of labor, such as the cost to lease space, the cost to buy equipment, things like that. So these are typical cost categories. And the reason you make these categories is that you tend to estimate each category in a different way. Here are some other things that you want to know in order to get an accurate effort estimate. The size, very helpful. That's why we talked about estimating size. Historical data. What has your organization done in the past? What is the schedule? What process or method or life cycle are you going to follow? What language are you going to use, and do your people know how to program in that language? What operating system are you going to use? Is it one that you know about and are familiar with, or one that is brand new or a new release that you're going to have to do a lot of learning for? What tools are available? How experienced are your people? These are the kinds of factors, and we're going to talk about more of these, that might influence your effort estimate. So let's talk about the effort estimating process from a very high level, and then we'll go into some details. From a high level, the first thing you want to do is to document what the tasks are, and that means for each task you have to know what does that consist of. Now, when we talked about the work breakdown structure, we talked about the basis of estimate and the work breakdown structure dictionary, which are ways of helping you document what each task consists of. But they're not the only way. Maybe you already know. Maybe one of the tasks is write the code for the driver or something. And you know what that entails. You don't need to write it all down and spell it all out. That's okay, as long as you know what you're supposed to do. Then you figure out the magnitude of each task. This is a 10-hour task. This is a 3-week task. And in some cases, you also look at the complexity. Because something that is 100 lines of code that is really simple might take less time and less effort than something that is 100 lines of code but extremely sophisticated and complicated, like maybe some kind of a telecommunications interface or something. You quantify the task based on the nature of the task. But basically you're saying, how big is it? Then you estimate the effort for all the software development tasks. And we're going to talk about many methods of doing that. Then here's where things are a little different than what you might have expected. Estimate it again using a totally different method. Why? Because most methods are imperfect. Most methods are inaccurate. And if you try it with 2 different methods, it will give you a lot of insight. For example, it might teach you that hey, there's a big difference between this method and this method, I got to figure out which one is right. If the methods give you different answers, you have to resolve the discrepancies. And resolving the discrepancies is where your creativity and your intelligence comes into play. Because this is where you say, okay, when I estimate using the first method, it comes out to be 1,500 hours. And when I estimate using the second method, it turns out to be 1,850 hours. Why is the second method quite a bit longer than the first method? And then you have to analyze the methods. What does each method assume? What does each method incorporate? What does each method not take into consideration? For example, maybe the first method assumes all the programmers are equal, and the second method has a factor where you indicate how much experience the programmers have, and you happen to have inexperienced programmers. Well, if that's the case, you might say, well, then the first method is probably too generous because it's assuming all the programmers are average, but my knowledge of what the second method does says, well, maybe it's because I have so many inexperienced programmers. The second method takes that into consideration. The first method doesn't. So that's what resolving the discrepancies is all about. And this is really where your skills come into play in step 5. But once you've decided that, typically what you decide to do is to increase one method, decrease another one, or maybe one or the other or both. Change some assumptions that go into the methods. And then you go back to step 3, redo each method, see if they come out about closer together or about the same. If they do, you can go on to step 6. If not, you keep going around this step 3, 4, 5 until the methods are similar in terms of the number they predict, or you decide you believe one of the methods and don't believe the other one. When you do assignment 4, which you probably won't worry about much until after the midterm, you're going to go through this process. You're going to estimate using 2 different methods, and then you're going to resolve the discrepancies between the methods and then do a second estimate where the 2 methods are much closer together. Anyway, what I just described is how you get the effort. We'll talk a little bit later about how you convert that to money. But then step 6, that's step 1 through 5. Step 6 is to estimate everything else given that you have agreed on what the effort is for the actual software development part of the activity. Because almost everything else is a function of that. For example, when you estimate the effort, let's say you decide you need 100 person months, and you've decided that you want your schedule to be 10 months. That's 10 people times 10 months, right? Well, if you decide you're going to go with 10 people, then that tells you how many people you have to train, how many facilities you have to support 10 people, how many computers you have to buy, how many copies of the compiler. You say with 10 people, here's how I'm going to manage it. Maybe you divide it into 2 groups of 5 each and have a manager for each, and therefore here's how much management cost I'm going to have. I don't know, I guess we aren't moving around enough. The light seems, there we go. Thank you for getting up. You turned the light on. Actually, the problem is the light switch is in the back row, and there's nobody in the back row. Anyway, so a lot of these costs will be estimated as a function of what your effort number is. That's why you do it this way. Now, let's talk about things that affect the accuracy of your estimate. Well, there's how much experience you have. There's how much data you have. There's how much information about the new project that you have. And then there's how much luck you have. And they all enter into the process. When you're writing a proposal or estimating a new project, it's very common to be at least 50% off. There's just too much you don't know. Now you try to know as much as you can, and you don't have to be 50% off, but it's not unusual to be 50% off. At the start of a project, after you've won the contract and settled on all the details and know a lot more than you did when you wrote your proposal, you can still be 20% off very readily. Many projects are at least that far off. So it's important to realize that you may not be highly accurate in your estimate at the beginning of a project. Many people don't like this idea, but it's part of reality. And part of the reason is requirements change. Part of the reason is your estimating methods are not necessarily accurate. But we're going to talk about some of those issues. Good historical data is one of the most useful things to help you. If you have good data from previous projects, it's very valuable in helping you make better estimates. As a matter of fact, if you try to bid on a contract from the U.S. government and you tell them, here's how big my software is, how many lines of code or how many function points or whatever, the government will tell you what they predict it will cost. How did they come up with that prediction? They've got thousands of projects they've had in the past, and they know what the data is from all those projects. Because when you do work for the U.S. government, you have to give them all this data at the end of the project. And so they can tell you what they think the estimate's going to be. And actually, one of the techniques they use is they have you do an estimate, then they do their own estimate, and if you're way off from theirs, they think you're trying to cheat. That's the way it works. Okay, to summarize this module, there's many ways to measure effort. The most important thing is to be consistent. Size and effort are related, but it's not a simple relationship. There's all sorts of other factors. The estimating process begins with estimating the software costs, and then once you've gotten that estimated, then estimating all the other costs. That's the end of the module, so we're going to take a break, and let's make, it looks like about an 8-minute break. All right. For those of you watching, we had the mic off, so I was just saying that this is the most detailed part of the course that we're about to go into. But before I do that, I want to do something else. I want to talk about Assignment 2. And before I even talk about Assignment 2, I want to talk about all the assignments in this course and where they came from. Back in, roughly 1985, I was put in charge of a software project. And I didn't know a whole lot about doing that. And I learned all kinds of things. And my assignments in this course are based on what I learned and what experiences were most instructive for me when I learned these things. You'll notice that Assignment 1, if you did it the way it's supposed to be done, required you to read all the handouts for the course and try to understand them and make sense out of them. That's exactly what I did back in those days. I was given a lot more material than what you had. Of course, I was working full-time also. And I had to plow through all these documents and try to make sense of them and figure out, how am I going to make sense out of all this? Assignment 2, again, benefits from you having looked at all the material and having tried to understand it and make sense out of it. And I don't expect you by the end of Assignment 2 to have totally made sense out of it all, which is why Assignments 1 and 2 don't get grades that count. They just give you feedback to help you understand where you're right on track and where you're not. So there's a rhyme and a reason for all these assignments. And there's a website, I think it's called ratemyprofessor.com or something like that. And I always like to see what I look. And I have two kinds of ratings. The first kind are the ones that say, this professor really makes you work hard. Avoid his classes if you can. The other kind say, I'm so glad I took this course because I learned so much. So from my point of view, I'm giving you your money's worth. You're learning a lot, but you have to work at it. But again, it's all based on my personal experience. So what I want to do is I want to talk a little bit about Assignment 2 because even though I haven't finished looking at everything, I have looked at enough that I have a pretty good idea of things that some people are and are not getting done correctly. And first thing I wanted to point out, well, let's see if I can figure out how to make this thing work correctly. Okay, it says here, this is a template. Whenever you see something in red, it is information to help you complete the plan. Remove all red text, including this text, before you turn in your plan. Some of you didn't do that. The red stuff is still there, which means you apparently didn't read this. Now, the first area where I noticed a lot of things is in the assumptions and unknowns. And I wanted to point something out here. It says, for Assignment 2, list any unknowns. You may start to fill in assumptions and risks, but these are not required until Assignment 5. I expect between 5 and 15 unknowns. Now, why do I expect between 5 and 15? Because I want you to filter out the ones that are relatively insignificant or that are repetitive. I once had a student who gave me 500 unknowns. It was incredible, but I don't want that. I want the ones that matter. But the other thing that I've noticed is that some of you are not looking at this like a software project. You're looking at this like a hardware project. And you're finding all these unknowns that have to do with whether the hardware is fast enough or whether the hardware is going to do this, that, or the other thing. And maybe a few of those are important if they relate to whether the software will be successful. But what I'm expecting to see in the way of unknowns is things that are related to the software. And there's plenty of things that I know you would like to know but don't know from the material I've given you. So this is one way I can tell whether you actually read the material, is whether or not you have a set of unknowns that reflects what you don't know. There are a number of things in there. For example, there are some contradictions. One person says this, another person says that. And that represents something that you don't know. You don't know which one to believe or whether either one of them should be believed. So that would normally translate to an unknown if it is going to affect your project. You're thinking about this from the point of view of, I'm the software manager, I have to make this project successful. What are the most important things that I don't know that I want to know about? Now, once you have identified those unknowns and figured out which ones really are important, then you can start figuring out what to do about them. For example, you probably don't know how much memory is needed for this application. But you're going to do assignment 3 where you're going to estimate the amount of memory. So once you're finished with assignment 3, you'll either be able to resolve that unknown because you will have done an estimate and have a reasonable confidence in your estimate, or you can at least make an assumption. My assumption is that it won't be any worse than this, or whatever it turns out to be. That's up to you. There are other examples, and there are about, I'd say, 8 to 10 things that I have, if you will, planted. And if you find half of them, you're doing okay, because most people don't find all of them. But at this point, when you're doing assignment 2, the focus is on the unknowns. What is it that you don't know that would make a big difference in terms of how you would run the project, how you would plan to do the project? For example, how this is going to have a lot to do with how many people I need to hire, or this is going to have to do with how much time I'm going to take to get it done, or whatever. As you work on assignments 3 and 4 and 5, you will resolve a lot of the unknowns, and in the cases where you can't resolve them, you will put in assumptions. Generally speaking, when you have an assumption, you end up with a risk. You may also have a risk if you think you've resolved an unknown, but your resolution may be incorrect. So the whole idea is the first place to look for risks is in your list of unknowns. At this stage, I don't expect you to have all the risks defined. I'm mostly focused on the unknowns for assignment 2. But I've noticed that some of you sort of totally missed all the software unknowns and had a whole bunch of things that a system engineer would be the one responsible for rather than a software manager. So think about it from that point of view. And of course, a lot of you have already turned it in, so I'm giving you a prediction of what you're going to see when you get the graded stuff back. But in any case, that's what I wanted to point out with regard to the unknowns. Now, with regard to the product, most of this information you can pull directly out of material I've given you. But when it talks about the software, I expect you to go a little beyond what I've already given you, because this is a software plan. I don't expect you to have a whole lot of information about the hardware and almost nothing about the software. Because think of this as the document you would give to a new hire who's going to work for you doing software. What do they need to know? They need to know a little bit about the hardware, of course, but they also need to know what your software strategy is. So think about that. At this point, I don't necessarily expect you to have a lot of risks, because we haven't talked about risks and we won't until another 3 or 4 weeks. But if you do put something down, I'll give you some comments on it and so forth. I do want to emphasize the importance of evidence. The reason evidence is important is because if you think something is a risk, it's probably going to require some kind of resources to deal with it. You're going to have to track it, you're going to have to manage it, you're going to have to put something in place to mitigate it. And although we haven't discussed a lot of that stuff yet, your boss is going to say, Why should I give you the money or the people or whatever to do that risk management? And you have to convince your boss that it really is a risk. And saying, well, it's been a risk on every project I've been on isn't very strong evidence. Whereas in most cases, I have very specific evidence built into those handouts. A document that says something that you look at and say, well, it says right here that this might be a problem. And therefore, that would be your evidence. The such and such document on page 3 says blah, blah, blah. That's your evidence. That's what I mean by evidence. Something that you could use if your boss was looking at this and saying, this guy wants all this money for risk management, and he's listed all these risks, but I don't believe any of them. The evidence would be what would convince the boss that it really is a risk, or at least might be. The description is just to provide a little more background information wherever. Similarly for the measures, I don't expect you to have much here, but if you do, I'll give you comments on it. Basically, the idea is, if you have a risk, what could you measure to tell whether or not the risk is getting worse? For example, if the risk was, I don't think I have enough memory, then you could measure how much memory you predict it's going to take and then track it through the project. But we're going to talk more about that later in the course. Now, in terms of the project, one of the things I want to emphasize is this integrated master schedule. For assignment 2, you're going to come up with an integrated master schedule that reflects the project as you understand it at assignment 2. Keep in mind the integrated master schedule is an integration of the software schedule and all the others. And you don't necessarily know all the answers at this point. And then for assignment 5, you're going to show a later integrated master schedule that says, now that I've taken the course and done assignments 3 and 4, I have new insights on this schedule, and I think it needs to look like this. And what I'm going to be grading when you do assignment 5 is whether your discussion of how it changed makes a lot of sense. Don't say, it changed because I thought I needed more time. That's not a very good explanation. A good explanation might be, after I did the estimate, I realized I was going to need at least 3 more months to do this, and I did such and such and such and such, and here's what I came up with. Okay, now a little bit about the organization. This is a software plan. That means the emphasis on organization should be on the software organization. Yeah, you might show the project manager and some other managers and a little bit of structure. But I don't expect to see one box that says software manager and then a box underneath that says 25 software developers. No, the whole point is this is a software plan. How are you going to manage the software team? And therefore, you should have more detail on the software part of the organization. Similarly, software positions and roles, I would expect somewhere around 10 categories. Maybe 15, maybe 5, but not 2 and not 30 categories of people. And the people that you're describing here are software people. Don't put in the project manager and a description of what the project manager does. That's your boss or your boss's boss. Don't put in the electrical engineer. That's somebody else. That's not the software team. You want the software group. You're going to have, let's say you're going to divide it into 4 teams, and you're going to have 4 team leaders and so many programmers and a few testers and whatever you're going to do. But it should be the software positions. That's why it says software positions. Okay. Let me see if I can find anything else that I wanted to emphasize, because most of you took a good stab at a life cycle, and a lot of you did a pretty good job there. But I want you to understand the difference between the rationale for the life cycle and the rationale for the process. The life cycle is the top-level picture. We're going to do waterfall. We're going to do an iterative thing. We're going to do agile, whatever it might be. Whereas the process is the gory details. and there may be some specific things you decided to do there, and you want to explain the reasoning for that when you discuss the rationale for the process. Okay, tailoring says, what are you going to do that's different for the normal, from the normal case? And we talked about tailoring earlier in the course, and the idea here is you are making the process fit the specifics. So let's say you decide, I'm going to use the waterfall process, but because of the particular characteristics of this project, I'm going to do something a little different from the way you would normally do it. That's what you would be putting in the tailoring section. Okay. Reviews. We haven't really got into reviews yet. We talked a little bit about it, but we're going to talk more about it. And again, I want you to think, at what point am I going to have a review of some sort, and what is it going to discuss, and so forth and so on. Let's see if there's something else that I noticed when I was looking at assignments 2s. The only other thing I wanted to point out for assignment 2 is that what a lot of you did on the work breakdown structure is it didn't make sense. The numbers didn't make sense. Normally when you have an indentation, the number system, well, we covered it in class, and it's covered in the handout called the Mr. Television Work Breakdown Structure. It's all described in there, and you don't have to do it exactly the way that handout says, but the numbering and the way you indent things should be pretty much the way it's described there. And I'll be giving you specific comments. But anyway, I just wanted you to understand what I observed when I looked at the things so far. And those were some of the main things I noticed. Okay, now we're going to talk about basic methods of estimating effort. Yeah? I'll put it this way. If you do, I will try to grade it, but I may be busy grading midterm exams or assignment 3s or something, so I'll get to it if I can. Similarly, when you turn in an update of the personal work breakdown structure, I look at it when I can, usually just to say, yeah, you're on the right track or you're not. Okay, we're going to talk about basic methods of effort estimating, and then I'm going to talk about a process for documenting and updating your estimates. So we're in the estimate effort box. The first method of estimating is very simple. You compare with your previous experience. So it's the first and most basic method of estimating effort. You take the size estimate and multiply or divide by the historical productivity depending on how you record it. So if you record staff days per line of code and your size estimate is in lines of code, you multiply. If you record lines of code per staff day, then you would divide. But it's the item in blue is your historical data. The item in black is your size estimate. And whatever your unit is, however you decide to measure the size, then you keep track of your experience in a certain way. Now, one of the handouts includes your organization's historical data, and therefore you can use that. Whatever you measure, historical data helps make this a more accurate method. Now, just to put these things in perspective, if you're writing in a high-order language like C++ or something like that, the typical numbers people get in lines of code per day are 2 to 30. If you're writing in assembly language, it tends to be more, but that's because each line of assembly does a lot less. It's actually less actual productivity. Generally speaking, if it's a very highly constrained project like safety critical real-time stuff, you tend to be on the low end of this scale. And if it's not constrained at all, like an application that doesn't have a lot of time constraints on it or something, you tend to be at the higher range. And you can even get higher if you have certain kinds of tools that help you develop it faster. So this is just very general ballpark numbers. The numbers I put in the materials are based on probably 10, 15-year-old ways of doing things. So they aren't necessarily the most modern, but for purposes of learning the technique, it doesn't really matter. Let's suppose in the past you have found 16 lines of code per staff day for complex software and 24 for simple software. And let's suppose your new project you estimate is going to be 8,000 lines of code. Then, and let's say you assume, based on your estimate of size, that the new one's going to be complex. Then you take the complex number, which is 16, and you get 500 staff days. That's how this method works. Now, the question is, how accurate is this? And the answer is not very, and here's why. This is typically where you get your historical data. Each red dot represents a previous project similar to the one you're doing. And most organizations, when they collect the data, they find a pattern somewhat like this. You notice that this project here got 24 lines of code per staff day. This one here only got 4.5. But if you look at it, you sort of see there's a slight upward trend, which presumably means your organization is getting better or more experienced or something, or better tools or something. And if you average them all out and follow the trend, you say this is about, on average, where I would expect the next project to be. But it could be way up here, it could be way down here. When you use historical data, particularly if you don't have a whole lot of data, there's a lot of uncertainty in your number. So, in fact, let's suppose the complex numbers varied from 8 to 24 lines of code per staff day on all those different projects. Then your estimate for the new one, you'd say, well, I estimated 500, but it could be as little as 333 and as much as 1,000. Now that's a pretty big range, 3 to 1. But it gives you some sense of what would be the best case, what would be the worst case, and what is the most likely. Remember, on size, we talked about the minimum, maximum, and most likely. Well, that's kind of what we're talking about here. If we do as poorly as the worst project we have data for, it'll take us 1,000 staff days. If we do as well as the best project we have data for, it'll only take us 333 staff days. And if we look at the average project, it's going to be 500 staff days. So that's how this first method works. You look at your historical data and then average it out and then look at the worst and the best cases and come up with your number. Historical data usually give you a range. The more data you have, the narrower the range usually is, which is why you want to collect lots of data. Now, what do you do about the fact that you know that this method is not necessarily precise? Well, plan to update your estimate. Say, okay, at this point we don't know much. We think it might be 500, but it could be as much as 1,000. Say, when we reach a certain point in our project, and exactly where that point is depends on where you think you're going to know something. Let's say you've got an iterative thing and you're going to go through 3 iterations. Well, you do, at the end of the first iteration, you'll have a pretty good idea of how that worked out compared to what you thought it would, and then you might update your estimate based on what you learned there. The second method of managing risk is to use more than one estimating method. That is because when you use more than one method, it gives you a better understanding of what the truth probably is. And the third risk management method is to set aside a reserve amount based on how much uncertainty is in your estimate. So in the case where you had, it could be as good as 333, but it could be as bad as 1,000, You might plan for 500, but set aside enough money that if it looks like it's going to be closer to 1,000, that you have enough money to pay the people to do the work. So that would be the third method. Now, you don't necessarily have to do all of these. You usually use some combination of these things. Here's an estimate. Method 1 gives you a number of 3,500. Now, if that's all you did and you went with that estimate, well, that might seem okay. But what if you do another estimate and the second estimate comes down to 3,000? Well, then that tells you that maybe I better plan on somewhere in that range. So you try a third method, and the third method is way up at 5,000. Now what do? Well, the point is you should be asking questions. Why is the third method so much bigger than the first two? And what does each method take into consideration? What does each method not take into consideration? And which method do I think is more accurate based on what I know? That's the whole idea of resolving discrepancies. You use more than one method and then try to figure out why they're different, and then try to figure out which one you have more faith in. Multiple methods tell you how much you don't know. They help quantify how much you don't know, so you can tell the boss how confident you are in the number. They also force you to ask questions. Why are the numbers different? What do I need to learn in order to get better information? And ultimately, they help you learn. Beware of averages. Let's suppose you had 7 methods and they came out like on this slide. What that probably means is that the 3 methods on the right made some assumptions or brought into consideration certain facts that the ones on the left didn't consider. And so you should be asking yourself, why did those 3, which are all kind of similar, have such a different number than the 4 on the left? You shouldn't just take the average and go with it. The average is almost sure to be wrong here. But if you try to understand what the different methods assumed, what factors they took into consideration, what factors they did not take into consideration, the usual result is you say, I think I trust the one on the right, or I think I trust the one on the left. Now, this is one of those slides that the notation on my computer uses a character set that is different from the character set that's on the computer at SMU, and I don't know what it looks like on your computer. This little symbol here is supposed to be a union, and this one is an intersection. And so if you take 3 methods, the most likely is the intersection. So if you take the intersection of these 3 ranges, it's this little blue line. It's this one to this one. It's the part that's in common with all 3. The possible range is the union of all 3, which means the furthest left to the furthest right. So that's what the red line represents. So what you're saying here is, if you showed this to a boss who understood these matters, you would say, I think the most likely result is in this range, but it's possible to be in this range. And that would help you with your risk management. When we talk about risk management, we'll see how you might factor that into your planning. All right, now let's talk about some other effort estimating methods. One of the most interesting ones, it's actually 2 methods. One is called wideband Delphi and one is called planning poker. They're essentially the same method, but planning poker is the shortcut version of wideband Delphi. The idea of these methods is to bring the expertise of multiple people together. We talked about that when we talked about using these methods for estimating size. Well, you can also use the exact same method for estimating effort. It's just that the information you work with is different, and the final result, instead of being an estimate of size, is an estimate of effort. So this is another category of method that you can use to estimate effort. Now, before we talk about the third category of method, which is model-based estimates, I'm going to start talking about that later. I want to go through this stuff on the right here. And I'm going to focus on that mostly in the next module, but I'm going to talk about it a little bit in this module. By the way, I just got an email about a month ago from a student who wanted permission to use the method that I describe in the remaining slides of this module because it was so useful for him at work, and he wanted to show my slides to his boss. So at least one student found it useful. Anyway, all right. Now, the idea of the stuff on the right is your effort estimate is the input to your schedule estimate, just as your size estimate is an input into the effort estimate. And I want to talk about the schedule estimate next, before I talk about other methods of estimating effort. And the reason I want to do it is that knowing what's going to happen on the right will help you with some of the things you decide for the model-based estimates. So we're now going to talk about the schedule estimate. And the method I'm going to use for estimating schedule is a particular method that I use, and it's not necessarily the only way to do it, but it's a way that you're going to do it in Assignment 4, and it's a fairly straightforward way that teaches you a lot about what's going on. So I call it estimation as a series of schedules. The issue you're trying to deal with here is you have a size estimate, an effort estimate, a cost estimate, a schedule estimate, number of people, staffing level that's called. And one of the things that happens is when you change any one of them, what effect does it have on all the other ones? Now, if you go back to this structure here, if you change the size estimate, then if you set up your formulas right in your spreadsheet, it'll change the effort estimate because one of the inputs to the effort estimate is the size. Similarly, if you change your effort estimate, it should impact the schedule estimate. But the problem is different parts of your effort estimate have different effects on the schedule. So the question is, how do you keep it all together? Well, one way you can do it is to get a tool, and we'll talk about some tools mostly next week, that will help you do all this. But the reason I want you to do it yourself in Assignment 4 is so you understand what's going on inside all these tools, so you know what you can trust and what you can be dubious about when you use a tool. And you should also understand how it works. It's kind of like teaching you computer science and teaching you how to program, and then later on in life you don't necessarily program that way, but you know what's going on. Okay? All right. I think of this as a framework for estimating that doesn't care what your size unit is, it doesn't care what your estimating method is, it's only a way to tie all the different parts of the estimate together. Okay, and of course it's very helpful when you do Assignments 3 and especially 4. So we're going to talk about generating a series of schedules and then having that be influenced by the effort estimate. One of the things that this process will allow you to do is look at staffing, or what's called shop load, which is who's doing what when. How do you assign work to people? How many people you need, how much money you need, how much equipment you need, and how much, when the cash flow occurs. In other words, how much money do you need the first month? How much money do you need the second month? Rather than just how much money do you need for the whole project. So it's a basis for making management decisions. The reason you want to know the cash flow is that sometimes on a big project, you don't get all the money all at once. You get the money for the first part of the project, and then if you're successful, you get the money for the second part of the project, and so forth. So you have to estimate how much money you need for the different parts of the project. Now, suggestion when you're studying for the midterm exam or for doing assignment 4, study the remaining slides of this module to understand the steps of the process. Whenever you see something in blue, it means when I go to the next module, I'm going to use the exact same word and it'll mean the exact same thing. And then look at the diagram here. This is a diagram of the sequence in which you produce schedules using the method I'm going to describe. You go through a series of 4 steps. The top level schedule is the schedule that's in your integrated master schedule. The schedule, the software schedule as it appears to the non-software people. What does the project manager see? What does the electrical engineer see? And it's usually like the high-level steps of your, what your life cycle model. What you're going to do in the remaining steps here is convert that from a very generic do design, do coding, do testing kind of a thing to something that says we're going to spend so many hours doing this kind of work and this kind of person is going to be doing it. So, and then eventually you'll get into we're going to spend so much money doing this on this month. So that's how you get from a high level, here's what we're going to do, to a detailed level, here's how we're going to spend the money. And remember, a couple of times I've mentioned that when you have tasks in your work breakdown structure, you break them into categories. Well, for purposes of my example, I'm going to use the 5 categories listed here, which I've explained once before. And if you don't understand it, send a question or something, but I explained it in an earlier module what these 5 categories were. Okay. Now, what I'm going to do in the rest of this module is give you the how to do this in 30 minutes. Then when I get to the next module, I'm going to talk about what you would do if you were going to spend a couple of days doing a much more precise version of this. So let's talk about the 30-minute version. Your boss sees you in the cafeteria and say, I want you to come to my office at 1:30 and give me an estimate. How do you come up with a number? This is how you do that. Okay? You have to start with 3 things: a work breakdown structure, a high-level schedule, basically whatever life cycle you've chosen, and your experience. Now, in assignment 1, you did a work breakdown structure for taking this class. In assignment 2, you did a work breakdown structure for the Mr. Television project and a top-level schedule for the Mr. Television project. So you have 2 of the 3. Okay? Now, here's how it works. The top-level schedule is something was developed as an early part of your planning activity. It may need to be revised, and in fact, your estimating process may give you information that tells you it needs to be revised, but it's a place to start. In this quick and dirty version of the method, the generic schedule is a step that is going to be skipped over. But in the next module, you'll see how we use that. And in this quick and dirty version, we're going to estimate everything in staff months. So here's how it works. The first step is we produce something called the base effort. Notice it's a blue word. It's going to be the same, it'll mean the same thing when we talk about it in the next module. It's what it costs to do software development only. And the way you do it in this quick and dirty thing is you have seen your work breakdown structure. You know how much you have to do. And you say, I think it's going to take me about 18 staff months to do the design and 22 staff months to do the coding and so forth and so on. I add it all up. That's my base effort. Now, this is a 30-minute version. So all you can do is say, based on my experience and based on the tasks I have to perform, I think I'm going to need this many staff months to do the basic software development tasks. Step 2 is produce is called the adjusted base effort. And what you're doing here is you're adding any additional tasks that the software people have to do that are not strictly speaking software development, such as supporting the requirements analysis effort that maybe a system engineer is doing, and supporting the system integration effort, things like that. So in this example, you've added a little bit more, and now you're up to 93 staff months for your adjusted based effort. Step 3 is called the total effort, which is the adjusted base effort plus all of the support tasks. And again, in this example, you're saying roughly 8% of this number is what I need for configuration management, and 10% for quality assurance, and 10% for management, and therefore it adds up to this. Now, this total effort is represented on something called the effort schedule. And what you do is you say, okay, 119 staff months, and you're going to see in the next module how that effort schedule represents this. But for the 30-minute version, you don't do that. You just say, we're up to 119 staff months of effort when you count in all the support functions. Step 4 is called the total labor. And what this does is it says, anything else we have to do that we haven't already included that is measured in effort or in labor hours. For example, on this project we have to do some non-standard documentation, we have to do a special audit, anything at all that is unique. If your project has nothing like that, then this turns out to be the same as the previous one. But if there's something else you have to do that wouldn't normally be something you have to do, this is where you add it in. And then step 5 is where you convert all this to money. And the way you do it is you take what you had before and multiply it by the average cost of an hour of labor. And again, you're doing a 30-minute version, so you just have some number. Let's suppose the average person developing software costs $150 an hour. Now, that may seem like a large number. You say, I never got paid that much. But keep in mind that includes overhead, vacations, and all kinds of other costs. Most companies will give you an hourly labor cost for software developers, and I'm just using $150 as an example here. And your usual reaction when you see that number is, boy, that's a lot bigger than what I get paid, but that's the way it is. So you multiply the cost per hour times the number of staff months or whatever, and you get a cost for labor. Now, this is probably in thousands of dollars, but anyway, then you add any other costs that are not measured in labor, like equipment, software you have to buy, computers you have to buy, stuff like that. And that's your total cost. And at this point, we have the total cost of the project. Now, this is a very, very rough estimate, but you did it very quickly. You started with your work breakdown structure and the information that you knew about what you had to do and your experience, and you came up with a number. Not precise, hard to defend, but if you have to come up with a number in 30 minutes, this is a way to do it. Okay. Now, let me give you an example of going through this process. Suppose we have a size estimate of 12,000 lines of code, and on average for a project like ours, it's 24 lines of code per staff day. And just to make the calculation simple, I assume instead of 19, we work 20 days a month, okay? So I multiply it all out, I get 480 lines of code per staff month, divide that into 12,000, and we get 25 staff months for the strict software development. That's the first step. So the software development tasks take 25 staff months, and with 20 working days per month, that's 500 staff days. Step 2, I have to do requirements and system integration, and let's suppose based on our knowledge, it's another 30%. So that brings us up to 650 staff days or 32 staff months. Let's suppose our schedule as planned is 12 months. So I divide that out and I say we're going to average 3 people per month. We're going to start up with only 1, and we're going to quickly build up to 3 and continue till the end, and maybe the last month we only need 2.5 or something. So this is what we call the effort schedule. It says, here's how many people we're going to hire to have working on this project each month. It's going to take us 12 months, and we're going to get 32.5 staff months. All right? Now, the next step is all the support tasks. Now, an important thing about the support tasks is that they add cost, they don't add time, because the support functions are done in parallel with all the development activities. So, let's suppose the support tasks all together add another 25%. So basically, we had 3 people. Let's say that brings us up to an average of 4 people, or maybe slightly less. But anyway, so what's called our total effort schedule has has basically 1 more person per month on the average, so that we get the higher total staff months. And that 1 extra person is doing all the support functions. The labor schedule is, now I'm going to break it down into a little more detail than I did the last time. In our company, we have 3 salary levels: new hires, average people or normal people, and senior people. And let's suppose the senior people make significantly more than the normal people, and the normal people make significantly more than the new hires. So what we're doing here is we're taking the same numbers that we had on the total effort schedule. You'll notice the bottom line is essentially the same, but we're breaking it down. We're saying, okay, we're going to have 2 people in the first month, but it's going to be 1 senior person and 1 normal person. In month 3, we're going to add another normal person. In month 4, we're going to add a new hire, and so forth. So the main difference between the effort schedule and the labor schedule is the labor schedule breaks it out by which kind of person is doing the work. And in this simple example, we divide people based on how much they get paid. We're not worried at this point about the specific skills they have. We're worried about how many people are we going to need and what salary range are we going to need to pay them. Now, there's a second part to the labor schedule, which is adding any additional labor that we haven't already accounted for. And let's suppose in our particular case, we have to add some extra people to do an audit that only happens in month 12. So we have to add an extra 2 people in month 12, which brings our total to 44 instead of 42 staff months. And so we just add another row to our structure here to show that we're going to have 2 people in month 12 they're brought in from some other project to do an audit. Maybe the customer requires a special audit. Step 5 is where we multiply it all by how much we pay people. And remember, in the labor schedule, we had different salary levels. So let's say the seniors get $10,000 a month, the normal $8,000 a month, and the new hires $6,000 a month. So, and the auditors get $16,000 a month because they're brought in from the outside and they cost a lot more. So we multiply it all out, and that sums out to $368,000. And not only do we have $368,000, but we can look at the labor schedule and replace the numbers that were on the labor schedule with how much money we're going to spend each month based on the number of people and how much they get paid. So we're still going to get our $368,000 here, but what we've done here is we've replaced the labor schedule that we had here with a schedule right here that shows how much money we're going to spend each month instead of how many hours of labor. Why would this be useful? Well, the bottom line tells us how much money we have to have each month to pay the people. If you're the manager, you have to say, I need $18,000 the first month to pay the salaries for the people who are going to be working the first month, and so forth for the rest of the project. Now, at this point, if you have any other costs, like you have to go buy some computers or do some travel or whatever, you can just add that to the total and get a grand total number of how much money you need. So in this example, I've added some money for computers and travel, which adds to the total and makes the total quite a bit bigger. But that's the particular example I'm using. Now, a couple of other things you could do along the way here. You could add overhead costs. In other words, the pay scale that you use could either be a total including overhead, or it could be the actual salaries, and then you add an overhead factor later. It's kind of up to you. You could calculate by week, by day, I use by month to make it simple because I want to make it fit on a slide. But if you were doing it with a spreadsheet, you could do it by week if you wanted to, or even by day. And you can add anything else that you need to add in at the appropriate point in this sequence. And another thing you can do is if it's a multi-year project, you can throw in an inflation factor. Assume the average employee gets X% raise at the end of the year, and you could add that in. So with this basic structure, you can add in all kinds of stuff if you think it's relevant. And again, I suggest you study this procedure, and once you understand these examples, then what I'm going to do in the next module will be a lot easier to understand. And again, remember the blue words, because those are the words that are the same in all these examples. Okay, to summarize this module, historical productivity data can be very helpful in estimating effort. It gives you ranges, however. I mentioned wideband Delphi, planning, poker, and other methods could also be used to estimate effort. And I gave you this process for coming up with a sequence of schedules and representing how many hours of labor or how many dollars are spent each month by each kind of person. Okay, that's the end of this module. We're going to take a 7-minute break, and then we're going to do the last module tonight, which is going to show how to apply this to a somewhat larger type of project. So we're going to take our break now. Okay, let's do Module 17. This is going to take that same estimation process and go into it in sort of one level higher in detail. And I'm going to use staff days for this example. So we're still in estimate, effort, and cost. And what I'm going to do this time is I'm going to go through this sequence of steps that are outlined in this diagram. And one of the things I want to point out is on the left are the different cost categories that I described. You'll notice that different categories come into the process at different steps. Also, this kind of explains where you are in your big picture process. It's your initial planning level when you're working on the integrated master schedule is when you come up with the top level schedule and deciding on your life cycle. Then when you start deciding on the details of your process, that gives you the generic schedule. Then when you start your effort estimate, you start doing the effort schedule. The labor types gives you the labor schedule, and the labor rates gives you the cost schedule. Now I should also point out that for assignment 4, you do not have to do all of this. And you'll see that later. You will only have to go part way through this process. And the reason is, if you get partway through this process, the rest of it will be just a matter of grinding a bunch of numbers. And I'm not going to have you do that because it's not going to teach you much, and it's a lot of extra work. So I'm going to, believe it or not, I'm saving you some effort. The generic schedule is a mapping of your process or life cycle to the top level schedule. And it's basically saying, what am I going to be doing when? When am I going to be doing design? When am I going to be doing coding? When am I going to be doing testing? And it serves as the way to adjust the schedule. The way this is set up, when you put all this in a spreadsheet, the generic schedule determines the length of all these other steps. You'll see how that works momentarily. The generic schedule says when I'm going to do each process task relative to the overall project schedule. And here's what a generic schedule looks like. This is a generic schedule for a waterfall life cycle. Here are the months. And here are the steps of the waterfall life cycle, and I've chosen one that has a preliminary and detailed design as 2 separate steps, just for illustration purposes. And I'm going to spend the first 5 months doing requirements, and starting in month 4, I'm going to start doing preliminary design, and so forth for the rest of the waterfall cycle. Now, I don't have enough room on the slide to show like 2 years worth of schedule, so I'm just assuming that it continues to the right, and you can imagine how it goes. And the idea here is that this number on the right is the total of all the numbers here. So what this means is we're going to spend months 1, 2, 3, 4, and 5 doing requirements, and of the total requirements effort, 25% of it will be done in month 1 and so forth. In months 4 and 5, we're going to be ramping down the requirements effort and starting up the preliminary design effort, and so forth through the rest of the schedule. Now again, this is for a waterfall, so we only go through each of these activities once, and this is how we plan to do them. And the reason you have this total number here, and the reason it adds up to 100%, is that you make sure that these percentages here add up to 100. And the way you do it is make sure that says 100. Now, this tells you During month 1, all the people I have working for me are going to be working on requirements. During month 2, same thing. During month 3, same thing. During month 4, I'm going to have some working on requirements and some working on design, and so forth for the rest of the cycle. It doesn't say anything at all about how many people yet. We haven't gotten there yet. This is the generic schedule. And all it's saying is, how does the process get carried out across time? Now, this row at the bottom that's a different color, I made it a different color to point out that this is a totally optional row where I've decided I'm going to show when certain reviews are scheduled to occur. And the reason I put this here is because when I'm working out all this part up here, I might decide, well, let's try to get this done before this review. Or in this case, I'm going to have the requirements ready by this point, but I'm going to not have the design finished, or whatever it might happen to be. You can add, if you do this with a spreadsheet, you can add as many rows like this you want to show other things that you might want to keep track of. For example, very often the project will have project reviews scheduled for certain times, and you may want to mark that on here just so you remember when they are. Okay. Now, here is a generic schedule for an incremental life cycle. In this example, we have multiple phases, and in the first phase, I'm going to do approximately 30% of the requirements work. In the second phase, which occurs in the next cycle, I'm going to do about 35% of the requirements work, and in this case, I'm probably going to have 3 phases or 3 cycles, and I'm going to spend such and such a percentage of the requirements in each cycle. Ditto for all the other steps. Now, as you can probably imagine, you can take any life cycle model you care to and map it out like this. All you have to know is what the steps of the process are and what you're going to do during which month. And you'll notice your life cycle here is 3 iterations, whereas here your life cycle is a waterfall. But the process steps are the same in each iteration here, which is why you break it out the way I've shown you here. Now, in this example, I did another example of an optional row, which in this case shows you which cycle you're in. You're in cycle 1 or increment 1 here, and then you switch over to increment 2, and then if we had more room on the slide and you moved over to the right, you'd see increment 3 further on down. Now, if you have multiple software items, which you often do on a big project, you usually almost always do, you could have a separate one of these generic schedules for each one and then add them together to get the total. Or you could just combine them all in one. For assignment 4, you're going to combine them all in one. It's just less busy work. The only reason you would have separate ones is if each software item had a dramatically different schedule. Then you might do a separate one for each. So that's the generic schedule. And all it does is it represents the process and the life cycle in terms of what percentage of the work is being done each month or each week or whatever of the project. Now the next thing is the effort schedule. And you'll notice that we had an effort schedule in the methods we talked about in the last module. It's the same thing, except in this case it's a much more detailed schedule. The effort schedule is a mapping of the amount of effort you're planning to spend to the process and the schedule. And whereas your effort estimate was like 873 staff months or something, here you're going to break that out by month and by phase of the process. In order to do that, you have to know two things. The first thing you have to know is for each phase of your process, what percentage is that of the total work you're going to do? Now, where would you get these percentages from? Normally, you would get them from having data from projects. You have 15 projects you've collected data from, and you say the average project spends 9% of its total effort on requirements and 14.3% of its total effort on this step, and so forth. I will tell you that the way I came up with these numbers is that I wanted the numbers on the next few slides to be nice, even numbers that I could easily put on the slide. So I did everything backwards, and this is the percentages I came up with. But these are not out of range. I mean, these are numbers that you might typically find on real projects. So the normal way you would do this is you would get these percentages by looking at past history and say, yes, we've done projects like this before, and on the average, we spend X% of our time doing this activity. Now, in an example here, let's assume the adjusted base effort is 2,100 staff days. Okay? That's our estimate. Well, we take that 2,100 and multiply by each of these percentages to come up with these numbers here. Notice how I said I wanted these numbers to be nice, even numbers. So that's how, if you take 2,100 times each of these percentages, you get each of these numbers. This is called the effort vector. And it says, if we have a 2,100 staff day project, then we're going to spend 200 staff days on requirements, 300 on preliminary design, 500 on detailed design, etc., if we have an average project. This effort vector is what we need to compute the effort schedule. And the way it works is very simple. You do a matrix multiply. Back in high school where you learn matrix math, this is where you use it. You take the generic schedule multiplied by the effort vector to produce the effort schedule. Now, this is what it looks like for a waterfall. Now, if you look at it and compare with the generic schedule for the waterfall that I showed you about 7 or 8 slides back, it looks almost exactly the same, except instead of percentages, we have numbers of hours. Or actually staff days, I think it is. Anyway, and the effort vector is here, and the total is here, and if you did it right, the total should match the effort vector. The way we got this is we took the generic schedule and multiplied by the effort vector. The details are in the instructions for assignment 4, by the way. The process consists of multiply each cell in the generic schedule by the effort to be spent on the corresponding phase from the effort vector. The result is the corresponding cell in the effort schedule. Okay. The next thing we do is we add in support tasks. Now, for purposes of illustration, I'm going to assume that the support tasks add another 300 staff days of effort, which is 14.3% of the total estimated effort. That's actually probably too low. On a real project, it's probably more like about 30% or 40% or maybe higher. But just to make the calculation simple, I'm assuming that all the support tasks, the configuration management, the quality assurance, and the management, is an additional 14%. So what I did is I took my effort schedule and I added a row for the support tasks, and that gave me the total effort. Remember I said the total effort was one of the blue words. I didn't put it in blue here, but this is the same total effort that I had before. Now, you'll notice the number of people that, well, the number of staff days of effort, pardon me, the number of staff days of effort. And these numbers seem rather strange. Well, they're strange for a reason, okay? Now, I showed it all as one row. You could just as easily show a row for management, a row for configuration management, a row for quality assurance, and a row for anything else that you might fit in this category. I did it as one row because I didn't have that much room on the slide. Okay, now what this says is that my total effort is 2,400 staff days. And it's 57 staff days in the first month, 57 in the second month, etc. Now remember when I said the average company assumes 19 staff days per month? So you divide each of these numbers by 19 to get how many people you need. The effort schedule tells you how much effort you're going to need each month. The head count, or number of people, is just the total effort divided by the availability, which is that 19 number. It's the number of days per month that people are available to do work. And it's basically whatever your company's number is, but it's usually around 19 or 20. So, if we have availability of 19 days per month for the average person, we take our 57 divided by 19, that gives us 3 people. So, our head count, or number of people, is 3, 3, 3, in this case 4.5, 6.6, etc. So, one of the things you can do when you do the effort schedule in detail, the way I've shown it here, is you can calculate how many people you need in a more precise manner than before. The one I did in the last module was kind of a rough guess. And what you're saying is, in month 1, I need 3 people, and it looks like 2.7 of them are going to be working on requirements, and the rest is going to be doing some support function, and so forth and so on. Now, when you only have 3 people, some of these numbers don't seem to make much sense. But what if you had 100 people? Then these would make a lot of sense in terms of how many people you need working on different things. Now, let's suppose this is what your head count graph looked like. Well, this is probably unrealistic. You have 3 people for 2 months, then you jump up to 9 people, then up to 10 people, then back down to 3, and then back up to 5. When you do your initial schedule the way I've just shown it, this is what you sometimes end up with. You end up with something that you couldn't really run your project that way. So, what would you do if this was your proposed head count? You'd probably say, okay, I need to do more work in month 2, less work in month 3, less work in month 4, a lot more work in month 5, and have it all come out to the same total number of labor hours, but a smoother curve, so I can do some kind of sensible staffing plan for my project. How do you change that? This would be what a smoother staffing plan might look like. How do I get from here to here? I have to increase the amount of labor I work in some months and decrease the amount in other months, right? Well, there's a very simple way to do that. I'll show you in a minute. But once you have a head count graph like this as part of your plan, then when you run the project, you can track what your actual numbers look like to see if you're on schedule, to see if you're following your plan. It's really simple to do. Now, this is all you have to do for assignment 4. Remember I told you only had to do part of the process for assignment 4? But I'm going to show you the rest of the process so you know what the rest of the process is. You are not required to do the rest of it for assignment 4. But I can guarantee you that one student in the class will do it anyway because they didn't pay attention when I was speaking. I also put that in the handout and in the statement of work, but somebody won't read that either. But anyway, by the way, how do you change from here to here? You use the generic schedule. That's what the generic schedule is all about. You up the percentages in some months and decrease the percentages in other months as long as the total is 100%. That's where you change the things, and then all the rest of it automatically gets calculated out. That's the reason you have the generic schedule, so you can make those kinds of adjustments. All right. Now let's talk about the rest of the steps so you learn what else has to be done. But you don't have to do it for assignment 4. There might be a question on the midterm exam, however, so you do need to understand it. But I'm not going to require you to do it because it's basically a lot of busy work to do the next few steps. The labor schedule is a mapping of your labor categories to your process phases. Instead of the effort, it's broken up by labor categories instead of by steps of the process. It looks a lot like the effort schedule, but the rows correspond to different categories of labor. It indicates how much money will be spent each month by different types of people. How many testers, how many programmers, how many of this, that, and the other thing. So the idea here is when you're recruiting, you not only need to know how many people you need, but you need to know how many I need of each kind. So that's what the labor schedule helps you figure out. In order to do that, you have to produce a table like this. Whatever your categories are, whatever it costs you for each of those categories, it's called the salary vector, and whatever the percentage of the total that you're going to use, it's called the labor distribution vector. Now, where would you get these from? Again, you look at past projects. You say, well, on the typical project, we need about X% senior people and Y% new hires and whatever, and you figure out what those numbers are going to be. And then this is either what you pay them, or this could be the total cost, including overhead costs. It doesn't matter. You can add the overhead type stuff in now or later. It's up to you. That's what this slide says. Now, what are the labor categories? One of the reasons I didn't require you to do this in assignment 4 is that every company has different labor categories. I've shown an example where it's purely by seniority. You could have it where it's by the job they do. Testers, and you could have senior testers and junior testers, or designers, new hire designers, experienced designers. At Raytheon, we used to have like 300 and some categories of labor, of which about 30 of them applied to software. And we would have a chart like this that had 30 rows, and we'd have to put in percentages and the salary rate for all of them, except in the case of Raytheon, the financial people would supply the numbers in this column. And the software manager would supply the percentages in this column. And the company had a standard set of categories. Well, every company does it differently, so that's why I'm saying I don't care what your categories are. The idea is whatever your categories are, you have to divide it up this way. You could do it by level of experience, by job grade, type of work performed, or some combination of those. I would say that in most situations, 10 categories is plenty. But who knows how your company does things. The labor schedule is the labor distribution vector multiplied by the total effort vector, which is the bottom line of the effort schedule. So this is a vector times a vector equals a matrix. And this is what it looks like. You'll notice that it looks very similar to the effort schedule, except that the numbers represent the number of hours spent by this type of person each month. And again, because the numbers here are small, you've got numbers that seem kind of small, like 5 hours on our very senior people are working for 5.7 hours in month 1. Well, what are they doing the rest of the time? Maybe they're working on another project or something. If the numbers here were bigger, this would probably make more sense. But nevertheless, the idea is you're getting an idea of not only how much money are you spending or how many hours of labor are you spending every month, but what kind of people are needed to do each type of labor. And therefore, this can help you in recruiting. You can figure out, okay, I'm going to need so many of these and so many of those, and I'm going to need to bring more of these people on in month 4 or whatever it is. The labor schedule tells you how much effort will be spent each month by each type of worker, and you can determine what kind of people to recruit. You can add any additional labor at this point. For example, I gave the example of the audit in the previous example. And you just throw another row in the bottom, or more rows if you want to get your grand total of your labor. And again, the total here should tell you how many hours. You notice the total labor here is exactly the same as it was on the effort schedule. Here you've added in additional things that weren't represented in the effort schedule. And this is just how many hours of labor or how many days of labor or whatever are going to be spent each month and what the total is. And then this is where they're going to be spent in terms of the kinds of people you're spending it on. How much effort will be spent each month by each type of worker. And one of the things it may illustrate to you is that you have unrealistic distributions. You can have, when you look at the graph, it may be way out of whack, or it may show that you've got totally unreasonable numbers here and there, and you have to rethink some of the things. You can get a head count from the labor schedule just like you did from the effort schedule, and it'll be almost exactly the same except for any additional stuff that you added. And you can also, if you want to, generate a graph by type of person so you can figure out exactly how many you need of each type. But I point out that that part of this method is not necessarily very precise. You have a lot of flexibility there. So this is sort of a general guideline. Anyway, that's the labor schedule. The final step, which again is not part of assignment 4, is the cost schedule. All you're doing is multiplying it out by how much you pay people to figure out what it's costing you. How much money will be spent each month by each type of worker, and you can add in other costs at the same time. So all you're doing is taking the labor schedule, which is a matrix, multiplying by the salary vector, which is a vector, to get the cost schedule, which is another matrix. And you end up with something that looks like this. And it looks exactly like the labor schedule, except that you have dollars or thousands of dollars instead of hours of labor. So you can see not only how much money you need each month, but where you're going to spend it, what you're going to be spending it on. And you can add, it says additional costs here. This is where you've decided, okay, well, in addition to all this stuff, I also have to buy some computers or whatever, and you can add additional costs in there if you want to. By the way, one of the handouts gives you all the gory details of this method for assignment 4. The cost schedule tells you how much money will be spent each month by each type of worker and the total cost per month, and it may identify unacceptable cash requirements. In other words, you may say, I didn't know I needed that much money in the first month. I was only planning to have so much money available. So you can understand that situation. And this might be what your bottom line dollars per month graph looks like. And you can look at that and say, does this make sense? Now, in many organizations, the software manager is not the one looking at these numbers. The project manager is paying attention to this number. The software manager is only looking at hours in most projects. But you ought to know what's going on. And the reason you ought to know what's going on is because they're going to try to pull tricks on you. I'll show you that in just a moment. It tells you the cost of the project, how much money you need each month, categorizing the expenses by category. You can adjust for inflation in the future. You can throw in interest if you have to borrow money and pay interest on it. All that kind of stuff is just adding more rows to this structure. And that's the whole picture. Now, I want to go back and tell you about something. Let's suppose that the person in charge of money on your project looks at these numbers and says, I need to find a way to cut the costs. I want to reduce the costs by 10%. Okay? I'm going to say more about this next week, or next time. Next week is spring break. Here's what they'll do. They'll go back over to here. In fact, they'll go all the way back to this one. And they'll say, you know, those new hires are a lot cheaper than those senior people. So they'll go in here and they'll say, let's up the new hires to 35% and knock the senior numbers down. That'll cause the total cost to go lower, right? I mean, in an extreme case, you could just get rid of all the senior people and just replace them all with clerks. Now you, as the software manager, know that that isn't going to work. You know that if you take all your senior people and get rid of them and replace them with new hires and clerks and so forth, that you're not going to be able to get the job done as efficiently because the senior people are better. They're more experienced, right? But you see, the financial people in your company, they think you're not smart enough to figure this out. So they will say, oh, we can cut the budget by 10% and they'll never notice by tweaking these numbers. So that's why you have to know what they're doing. If they change these numbers, and we're going to see this next time, you have to recalculate your estimate based on the fact that you don't have as many experienced people and therefore your productivity is lower. And that's going to mean your numbers get higher and it's actually going to cost you more. But sometimes you have to pay close attention to what's going on, because here's what goes on. Let's say these are the numbers you turn in, and the project manager is trying to negotiate something with the customer, and the customer says, if you can cut the cost by 10%, I'll give you the contract. And they say, okay, I'll just cut the cost by 10%, and here's how I'll do it. You have to be aware of the fact that they're doing that so that you can protect yourself. You can at least know what they're doing. You may not be able to stop it, but at least you know what they're up to and you can try to defend yourself. You can try to show them why it's not going to work. You can at least put it into place some kind of a risk management plan to deal with it. So that's the reason I brought that up, and I'm going to say more about it next week. Anyway, that's the end of this module, and it shows how all this works. And let me just say before we go that what I just spent time on tonight is sometimes kind of challenging to understand, but when you figure it out, you'll be able to do assignment 4, and you'll have a really good understanding of what goes on inside all of these estimating tools that we're going to talk about next time. These tools all look like this inside, except they might be different in details. But this is the kind of stuff they're doing. And by understanding that, you'll understand what you're dealing with when you get a tool to help you estimate, and it spews out all these numbers that look so great on a spreadsheet, but that doesn't mean they're any better than what you could have done yourself. Okay, that's the end of tonight's lecture. And next week you have spring break, so you can study for the midterm, or you can work on assignment 3, or you can do whatever you want to do for spring break. And I'll see you in 2 weeks.